Hey guys, Mr. Mars here again. So this is our lesson on symmetry. There's two different types of symmetry, so you're going to see me floating back and forth between the paper that you have and some examples that I have up here on the board. So the paper that you have is in your packet. I believe it is page 20 that you should be looking at, but I'm going to be using some of these examples up here as we go along as well. So if we go back here to page 20, we'll fill in some information right away. So the two types of symmetry we're going to talk about today are called line symmetry, and we also have what's called rotational symmetry. So I'm going to split these up. We'll talk about them, separately, but let's get the notes part of it up here taken care of. Then we'll fill this out in a few minutes, okay? So first of all, line symmetry is a reflection. So probably just type that in. A reflection across a figure that carries the figure so that it lands onto itself. All right, so we need it to land onto itself. Okay, so you've done this before. Like if you take a piece of paper and you fold it in half, hot dog style or hamburger style or whatever you want to call it, we line up the corners like that and we crease it. That crease, that line, that crease that you have in the paper, that is a line of symmetry, right? That is your line that you are folding across. So for example, if I were to grab a piece of paper like this, right here, take this, I was to fold it like this, right? The original is right here, and I do my little crease right there. So here's my original piece of paper, right? This is my line of symmetry because if I put a line straight down the middle like that, these will fold, and the corners, the vertices, the edges will all land right on top of each other. Now we also know we can fold it the other way. We can fold hot dog style and stuff like that. But we don't always deal with just rectangles. We don't always deal with just shapes that look like that. So we're talking about different shapes, what their line symmetry is, and we're also going to talk about rotational symmetry, which rotational symmetry is where you turn the object. Okay, so I'll come back to rotational symmetry in just a couple minutes. So I want to specifically talk about line symmetry. Now again, this is one that you've probably done a bunch. So I'm going to start over here with these guys that we have over here, and I'm going to do some line symmetry. Now, I have specifically, I'm going to put a nice big fat juicy line right down the middle of the page right here, okay? And the reason I'm doing that is because everything over here that we're looking at, these are what are called regular polygons, okay? Now, if you don't know what regular polygons are, we've actually talked about them before. A regular polygon is a polygon that all of its sides are the same length and all of its angles inside are exactly the same measurement as well. So if you talk about a regular four-sided object, that would be called a square. All sides, all angles are equal. Regular triangle, that would be an isosceles triangle. Here we have a regular hexagon, so that's 6 sides, a regular pentagon's over here, and a regular octagon over here, okay? The reason I want to talk about these guys first is because their lines of symmetry are very easy to figure out how many lines of symmetry they have. Because if you look, and I go to cut these in half, and I can do it with a square. I'll start with the square first, because that's usually kind of the easiest one. Most students realize that if I take a square and I go like this and cut it right down the middle like that, I can fold that and it would land on top of itself, right? And then I can cut across like this. That would be another way, right across the middle, that would fold on top of itself. And a lot of people will also notice that, hey, wait a minute, you can go diagonal on these. You can go across diagonally like that. Those corners will fold up like that. And I can go diagonally like this, and those corners will fold onto each other as well. Right? So if we look, and we actually look at these as actual lines, we're not talking about little segments here, we're actually talking about complete lines, right? So I have, this is a complete line all the way across, this is a complete line all the way across, this is a complete line all the way across, and this is a complete line all the way across. Right? So I have 4 lines of symmetry. And so I open up here, these have 4 lines of symmetry. Right, we're good? So we got 4 lines of symmetry. How many sides were there? 4 sides. I come over to my triangle, equilateral triangle. I can go 1, right like that, that will fold in half. If you were to turn the triangle, you realize, hey, I can go this way, those will fold in half, and I can come from this corner over here to the opposite side, and that will also fold in half. An isosceles, equilateral triangle has 3 sides. All the sides are equal. Regular triangle, it has 3 lines of symmetry, okay? So if I move on to these other objects, over here I have a regular pentagon. Pentagon has 5 sides. You count them, right? 1, 2, 3, 4, 5. If it's a regular pentagon, guess how many lines of symmetry it's going to have? It's going to have 5. Those 5 are from corner to opposite side, from corner to opposite side, corner to opposite side, corner to opposite side, and then corner to opposite side. I didn't do a very good job on those, I apologize. But you get the idea. That's going to be cut into 5 equal parts where you can fold those over and they're going to land on top of each other. So this one has 5. If I move on to my hexagon, My regular hexagon over here has 6. I go side to side, I go side to side, I go side to side, and then I go vertice to vertice, vertice to vertice, and vertice to vertice. And that has 6 separate lines. So it's going to have 6 lines of symmetry. And can you guess how many our octagon is going to have? An octagon is an 8-sided object. It's going to have 8, right? We're going to go vertice to vertice. Kind of messed that one up. Vertice to vertice. There's 4 of those. And then I'm going to go side to side, side to side, side to side, and side to side. And there will be 8 of those, okay? So anytime we have a regular polygon, if it says regular in the title, it says it's a regular hexagon, 6 lines of symmetry. Regular pentagon, 5 lines of symmetry. You get the point, okay? Now what if it's not? What if it's not a regular polygon, right? What if it looks like this? These guys don't have all the sides aren't the same, all the shapes aren't the same. So I need to have something that's going to be able to, can I cut it in half? Can I cut it so that it folds and it lands on top of itself, okay? So I don't normally do this, but I'll do it today since we got you on video, okay? I'm going to take this same piece of paper I had a second ago, right? And I'm going to turn it into a parallelogram. So it's going to kind of cut like this. I'm going to do my best to turn it into a parallelogram, right? So I got like that. I'm going to cut like that. I'll let that fall to the ground, right? And then I'm going to come over here, and I'm going to cut this one like this. And I'll go up to this corner right here. We'll let that fall to the ground. All right, so I got myself a parallelogram, right? Now, here's the deal. A lot of students think, oh, no, you can't fold it that way, right? Because those don't match up. So they're pretty good with that. They're like, nope, you can't fold it that way. Those sides don't match up either, Mr. Mars, that's good. But the one that a lot of people think will work, that students think we can do, is they think that with the parallelogram, we can do this. We can cut across like that. But I want you to watch. If I'm doing that, I'm going from here to here, and I'm going to fold that. Watch what happens with the paper. When I fold that, these corners, these sides do not match up, okay? There is no line of symmetry that you can have for a parallelogram. This has 0 lines of symmetry. There isn't a line that you can put through there that's not going to actually fold over onto itself. Well, what about our trapezoid over here? Well, it depends on the trapezoid, all right? It depends on the trapezoid. So this trapezoid over here, there is no line of symmetry. I can't cut across this way, because if I come across this way, this will fold down to here, but this one's gonna land right about here. They're not gonna match up. I can't fold back the other way, right? I can't go this way. So move that back here. Come on, move, there we go. I can't come down like this, because while this may go here, this one's gonna land short over here, right? So there is no line of symmetry for this one over here either. So we had 0 lines of symmetry over here. We had 0 lines of symmetry over here. Well, Mr. Mars, does that mean that if it's not a regular polygon, it won't have any lines of symmetry? No. The isosceles trapezoid does. Now, the reason this is called an isosceles trapezoid is because these 2 sides right here are the same. And since those 2 sides are the same, we can actually take a line right down the middle right here. This will fall and hit over here. This one will come and hit over here, and everything will fold over. So it has, one, I can't go horizontal, because that's going to hit the middle. I can't go diagonal, that's not going to work either. But it does have 1 line of symmetry. So as you're looking at lines of symmetry here, you're looking at, can we cut these things across? Can we get those lines that are going to work out? Regular polygons will always have however many sides there are, that's how many lines of symmetry. So let's go back to your actual paper that you guys are doing. Okay, so I'm going to come back over here. So if we look over here with a rectangle, we talked about this. My rectangle, if I look at it, right, we didn't do this one, it's not a regular. So I'm going to come back to that one in just a second. I want to look at the ones that are regular, like our square. Square has 4 sides, right? It's going to have those 4 lines of symmetry. If I come down here to the bottom, scroll this down a little bit, I come down here to my regular pentagon. A regular pentagon has 5 sides. It's going to have 5 lines of symmetry. Remember, those were 1, 2, 3, 4, and 5, right? And my regular hexagon has 6 sides. It's going to have 6 lines of symmetry. 1, 2, 3, 4, 5, and 6 lines of symmetry. Okay? Those are our regular polygons. Now, isosceles trapezoid, we talked about just a second ago. Remember, those sides are equal, so we had 1 that went down the middle. Trapezoid, we talked about, there was no way that you could get trapezoid. This one has 0. There's none that are available. Parallelogram, we said parallelogram. I showed you with cutting the paper. There's no way. Those aren't going to work. That has 0. But what about a rectangle? Okay? We come up here to our rectangle, which was the first one. It has, how many do you think? It's not 4, because remember, that's a regular, and this is not a regular. A rectangle actually has two, and you guys probably have seen this before. We can cut it that way, fold it in half, that'll work, and we can cut across this way, fold it in half, that'll work. So our rectangle has two lines of symmetry, okay? Now, those are lines of symmetry. The next thing we're gonna talk about is called rotational symmetry. So I'm gonna go back to that other page for just a second, but first I wanna type up what rotational symmetry does. So if you look up here at your top, a rotational symmetry is a rotation, okay, that maps a figure back onto itself. Now, this is a little different than the other one. The other one, you folded it so it landed on itself, right? The corners all had to match up, and the lines had to match up, and the vertices had to match up. But with a rotational symmetry, that's a little different. So I'm gonna come back over here to these guys, right? I'm gonna take away our line symmetry real quick. So let me erase this over here, get rid of those lines, okay? I'm gonna do something real fast because I didn't realize it was gonna erase, so that's okay. So I'm gonna erase all these lines over here. I'm gonna erase this, I'm gonna erase this, and I'm gonna take that 0 over there and erase that guy over there, okay? And as a matter of fact, I'm going to real quick come over here. Oops, go to this guy right here, come over here, and I'm going to grab, where's that? This guy right here, and I'm going to put in a rectangle over here for our purposes for the rectangle, okay? Give me just a second here. I'm gonna do the following. I'm gonna put some little dots right here. Okay, the reason I'm putting those little dots, you guys, is because in just a moment, we're gonna rotate these things. And when I rotate them, oh, that one won't work. But when I rotate them, I want to be able to see where I started. So if you give me just a second here, I'm gonna do this. I'm gonna lock these guys in, do that guy and lock him in, do this guy. Look at Mr. Mars, lock it in. Just like I told you guys, second quarter, you're gonna start locking in, right? Just a second here. Where's that? There it is. Okay, this guy up here, same thing. This guy over here, same thing. And then this guy down here. And there we go. All right. Thank you for your patience on it. Sorry about that, you guys. You can fast forward that part if you had to. Anyway, so here's what rotational symmetry says. So rotational symmetry says, I'm going to turn the object, and every single time the object looks exactly the way it does right now, minus those little black dots. Those little black dots are just to let us know when we got all the way around. So all the way around, we're going to go all the way around 360 degrees, and every time it looks exactly the way it does, we're going to count that as 1 until we get all the way around to 360 degrees. So I'm going to start off with this little triangle right here, right? So I got my triangle, and I'm going to rotate 360 degrees. So ready? So this bar is going to be down here at the bottom. So ready? I'm going to rotate. Okay? How many times does it look like it did before? There's 1. Now I've not gone 360 degrees yet. There's 2. And when I get back to here, 360 degrees, that's the 3rd time. So in 360 degrees, it looked the same as it does right now 3 times. Okay? So I'm going to come over here. Now remember, these guys are regular polygons. This happened 3 times, right? 360 degrees happened 3 times, right? I'm going to come over to my square. Ready? My square, my regular quadrilateral, my square. Same thing. Ready? We're going to go around. There's 1. There's 2. There's 3. And there's 4 times. So in 360 degrees, it happened 4 times that happened, okay? These are, remember, regular polygons are a little bit different, you guys. So ready? So my pentagon, think for a second, how many times do you think it's gonna happen? You're probably right, so let's look at it. So ready? We're gonna go 1, there's 2, there's 3, there's 4, and there's 5. Now, I don't have a perfect pentagon, I apologize, but you guys get the idea. So that happened 5 times. So I'm gonna put it in here 5 times. Guess how many times it's gonna happen on my hexagon, which has 6 sides? It's gonna happen 6 times. Guess how many times it's gonna happen on my octagon that has 8 sides? It's gonna happen 8 times, okay? So that's how many times it looks exactly the way it did when you started. So how do I determine its rotational symmetry? Well, we run around 360 degrees, right? So I come back over here and I say, okay, I'm gonna take 360 degrees and I'm gonna divide that by 3 because that's how many times it happened in this triangle, right? So if I divide 360 divided by 3, I get 120 degrees, which means every 120 degrees that I turn that thing, it's going to look exactly the way it did. So it happens at 120. If I add another 120, that's 240. And if I add another 120, that's 360 degrees. It happened 3 times, at 120, at 240, and at 360, okay? If I come to my square, I do the same thing. My square, I take 360, I divide it by 4. That is 90 degrees, which means every 90 degrees, this will look the same. So if I rotate it 90 degrees, looks the same. If I rotate it 180, looks the same. If I rotate it 270, looks the same. And if I rotate it 360, it looks the same, okay? 5, comes same thing. We're doing the same exact thing. Divided by 5 is 72 degrees. Every 72 degrees, that's gonna look the same. So that's a 72, that's at 144, that's a 216, that's a 288, and that's at 360 degrees, okay? All of those are the rotational symmetry for a regular pentagon. So you can say to somebody, hey, listen, if you rotate that thing 288 degrees, it's gonna look exactly the way it does now. If you rotate that thing 216 degrees, it's gonna look exactly the way it started right now, okay? Number 6 over here, we're gonna take 360, we're gonna divide it by 6, that's gonna give me 60, so it's gonna happen at 60, it's gonna happen at 120, it's gonna happen at 180, it's gonna happen at 240, it's gonna happen at 300, and it's gonna happen at 360 degrees, okay? So if I were to ask you, hey, is 190 degrees a rotational symmetry for a regular hexagon? Your answer would be no, because 190 degrees, it's not gonna look exactly the same. It's gotta be one of those. And the last one I'll do real quick over here is we got 360 degrees, we're gonna divide it by 8, that's gonna be 45, so it's gonna happen at 45, 90, 135, 180, 225, 270, 315, and 360 degrees. That is our octagon. So it's gonna happen the same way. By the way, if you wanted to know the rotational symmetry, ready? How about this? What if I asked you what's the rotational symmetry of a 30-sided regular polygon? 30-sided regular polygon. Then you would take 360 divided by 30, and that would be 12. And so every 12 degrees, it's gonna look exactly the way it did before, okay? If I asked you what is a 10-sided regular polygon, like a regular decagon, 10 sides, then you take 360 divided by 10, every 36 degrees, it's gonna look exactly the way it did before, okay? So that is if you have a regular polygon, all right? Now, if you don't have a regular polygon, well, then we have to actually go do exactly the same thing we did over here, but we gotta see how many times it looks exactly the same as it did before. So when I come over here, we'll do my parallelogram, right? So my parallelogram right here, when I go to rotate it, I'm gonna go 1, that doesn't look the same. Notice long sides on top and bottom, short sides are on the side. That doesn't count, that's not 1. 1, 2. It happened 2 times, right? It happened 2 times on this one. So I would go 360 divided by 2, that's 180. So it's gonna happen at 180 and it's gonna happen at 360. That's my rotational symmetry for a parallelogram, okay? Come up to my isosceles trapezoid up here, okay? Ready? My isosceles trapezoid. Remember, dots at the top, short side top, big side bottom, okay? Zero. It never happened, right? It never happened. So this is considered actually to have no rotational symmetry. It does, it has 360 rotational symmetry because it'll happen at 360 degrees, but everything happens at 360 degrees, right? Everything's always gonna be the same at 360 degrees. So this is considered to have no rotational symmetry because it will not happen in less than 360 degrees, okay? So if I come over here to this guy, right? My regular trapezoid, if you do this one, now I can't spin this one because the way it's set up, I couldn't get a picture for that one. This one is never gonna happen either. So this one is also gonna have 0 rotational symmetry. But what about my rectangle down here, right? So my rectangle, ready? Rectangle, that's not the same. There's 1, not the same, and there's 2. So my rectangle also has 2, so I would take the 360, I would divide it by 2, I get 180 and 360. Those are my rotational symmetries. So going back to our page that you guys have in front of your notes, we're going to do the same thing. Remember, if we were to take this and spin it around, we talked about this, it's going to happen 2 times. So we're going to take 360, we're going to divide it by 2, that was 180 and 360. Those are my rotational symmetries. This one, my square, remember that's a regular polygon, so it happened 4 times. So that's where we went 360, we divided by 4, that gave me 90, so it happened at 90, it happened at 180, it happened 270, and it happened at 360 degrees, okay? So these are the same ones that we did just on the other side. I'm gonna let you guys finish the rest of these out because I don't need to keep going through these. You can finish this out from the video that I did earlier because each one of these is up there, the trapezoid, the isosceles, the regular pentagon, hexagon. You're gonna fill those out. And then for tonight's homework, you're gonna come over and you're gonna answer these questions over on this side over here, okay? Hope you guys had a great day with the sub. Hope everything went well. I look forward to seeing you guys tomorrow, and good luck.